Hello, hello, welcome. Let's go ahead and get started. It's 10 after 4. Welcome to the SoC cluster idling talk. This is part of a project that the Power Management Working Group of Linaro is working on. We're going to kind of do a shared presentation here between myself, my name's Kevin Hilman, and Hansson and Lina Iyer are going to be kind of sharing this talk to kind of cover the topic. So the first part I will do, it's kind of a review or a redo of what I presented or what we presented at Linux Plumbers a month or so ago. We were trying to make a bit of a pitch to the crowd at Linux Plumbers of kind of rethinking a little bit of how the idle management in the kernel is working for CPUs. And so we have some ideas, and we were making a proposal at Plumbers. So this is I'll just kind of quickly go through what we did at Plumbers and what we talked about, and then we'll finish off by talking about some of the next steps we discussed with a bunch of the folks at Plumbers as well. So right now in the kernel, there's two different ways of managing idle. We manage idle for CPUs and we manage idle for I/O devices in two completely different ways. Right? For CPUs, we have CPU idle framework and a few other APIs. And for I/O devices, we have compared to CPU idle, relatively new framework called runtime PM in the kernel. It's not that new, but it's new relative to CPU idle. And so these two frameworks kind of live in two separate worlds. You use one for CPUs and use the runtime PM for everything else. And so a combination of things, the fact that we're doing these two different ways, but also the fact that the CPU idle framework itself is not scaling well. It's not scaling well for certain types of SMP, and it's definitely not scaling well for multi-cluster. And so we're kind of exploring why not use or find a way to combine what we're doing for I/O devices for CPUs as well. So basically for the I/O devices, it's very runtime PM centric. Runtime PM is basically, it's a generic framework for essentially declaring when devices are busy and when they're not busy, and then letting core code manage the idle states for devices. So you can think of, if you're familiar with CPU idle, you can think of it like CPU idle, but it's slightly more complicated and has a few more features that CPU idle doesn't have. But for us, the main goal was thinking about what if we could combine these? What if we could combine the two? And basically, what if we started using runtime PM for CPUs instead of using CPU idle directly for CPUs? And part of that is in modern SoCs. The other thing that CPU idle is not managing well is the concept of power domains and hierarchical idle states. When you have multiple CPUs, multiple clusters, you have I/O devices inside power domains that are shared with CPUs and that type of thing. We're not managing that well with CPU idle. And in various vendor trees, people are doing it in all sorts of interesting different ways. And so we're trying to propose a way to make that a little more general, especially when we have a framework like runtime PM and the generic power domain framework that's already describing this for I/O devices. We're exploring whether or not to do that for CPUs as well. So yeah, for example, for a CPU is typically in a power domain or shares a power rail at least with a bunch of other CPU connected, what I just call stuff here. So like GICs and floating point units and local caches and things like that, which all are power gated together when a CPU hits a low power state. And so the generic power domain was basically was designed to deal with this type of thing for I/O devices. So why not use that to describe CPUs and their other connected peripherals? And at a higher level, we could even take the power domains in the kernel can actually be nested. So we can use that to describe, not only use a power domain to describe a CPU and some of its connected IP, but you could nest those power domains inside a bigger power domain, which could then represent a cluster. And so on, keeping going up to have clusters plus interconnects and things like that. So we can use genpd essentially to model the hardware, basically how the hardware is designed, and model the hierarchy of the states. So in that case, the cluster could be modeled with a generic power domain that includes the CPUs, the shared cache, and things like that. So yeah, so this is just kind of, I mean, the structure of genpd actually fits really well with how the CPUs are structured in hierarchy on most SoCs. So we're basically exploring how to do that, and well, first whether to do it. The discussion at Plumbers was basically whether to do this, and as well as how to do this. There's a little bit of pushback, but in general, there was basically pretty strong agreement this is a good direction to go. It makes a lot of sense in terms of framework. There's a lot of devils hiding in the details with locking and races and things like that, and how to actually do these implementations, but that's stuff we're exploring right now. So yeah, so Lina, do you want to take it from here? So that's kind of the big picture where we're going, and then Lina's going to talk about some of the stuff that she's been proposing for the implementation details.
So this is a picture of what the implementation is going to look like. So in this particular case, this is a big little CPU. You could see 4 CPUs on each cluster. And then there are common domain elements like the L2 cache, and I've just explained L2 cache here, but then you could have buses and you could have PLLs and a bunch of other things that are part of the domain, and that support the CPU in that particular cluster. So when there are 2 clusters, and when both the clusters are in idle, you could actually power down the entire domain. So when the CPUs go down, the CPUs are generally controlled by CPU idle, and when all 4 CPUs all 4 CPUs are in idle, you have an opportunity to power down the entire cluster. That means turning off the cache, turning off the PLLs, reducing bus clocks and everything else. And when both the clusters are down, you could actually power down the entire coherency interface as well. So that helps you save quite a bit of power in the runtime non-suspend use case. So to summarize what Kevin just said, what we need to do cluster idle is a framework that's capable of providing a hierarchical layout. It should also support nesting. One of the biggest things with cluster idle is figuring out when do we actually power down the cluster. So the last CPU going down powers down the entire clusters. The last CPU in the entire system powers down the entire system. But there could always be a race condition between the last CPU going down and the first CPU coming up. So a framework should be capable of providing synchronization between these 2 entities. Also, different SoCs are going to have different ways to power control their domains. And so there should be adequate platform callbacks so that the SoCs can do SoC-specific activities. And an ability to do this from CPU idle and hot plug. Hot plug is a very obvious use case. When you have all the CPUs powered off, you should generally be able to turn down the domain as such. But for CPU idle, when all 4 CPUs are powered down by CPU idle, there is a small opportunity, but this small opportunity adds up towards the entire battery life of your device. So doing this from CPU idle is also very important. And a relationship in a DT. Not all SoCs are going to have the same 4 CPUs in each cluster, 2 clusters, and a big coherency domain. They're going to have multiple CPU configurations that could be multiple domains, and this can only be explained correctly in the device tree. So an ability for a framework to do this in the device tree, read it from the device tree, and provide you the complete hierarchy is very desirable. So what we have as a solution is to use genpd and runtime PM. The CPUs, so you describe the CPU domain consumer and the CPU as a domain consumer and a genpd domain provider in the device tree. So the device tree specifies the relationship between who is providing power and who is the domain controller for a particular set of CPUs. And then this domain controller can be nested within another domain controller. So the device tree, genpd lets you do this in the device tree today. So you already have an established way to represent the hierarchy of devices in the device tree. So once you have these things set up in the device tree, you initialize a genpd object from your platform code by calling into the genpd framework, and you attach CPU devices. This is how you do it with any generic CPU, any generic device. So you would attach a CPU device to the genpd, and what we have added in addition to that is an ability from the CPU idle and the hot plug call path to call into runtime PM. So every CPU device that was added to the domain would be invoked from the CPU idle and the hot plug call path to say, hey, this device is no longer in use. So when the device reference count goes down, and ultimately there are no more devices left in a particular domain, the domain will also get powered. At which time, the domain will give a call back into the platform driver, and the platform driver can make probably write to the registers that will actually power off the domain when all CPUs go down. So the genpd framework as such is not without problems. The genpd framework was written with a domain that's domain for a device that's capable of powering in and powering out slowly. So as a result, we have used mutexes, and so the domain, powering on a domain is generally, you have to power on a regulator, and that might actually sleep. So we've used mutexes so far. CPU idle runs with interrupts disabled. So when you have interrupts disabled and then you call into genpd, where you lock a mutex and then you go into sleep, it's definitely not a workable scenario. So we have to convert genpd to use spin locks to use it with CPU idle. But not all domains want to use spin locks because spin locks are expensive, and they idle the CPU or they spin the CPU waiting for a lock, which can be performance intensive. So what we have is an ability for a genpd domain at initialization to say, do I want to use spin locks or do I want to use mutexes? We have done this in the reg map. This is the same mechanism that we are using here today. It's domain specific. The domain determines using a flag saying, are you going to be IRQ safe or not? Another problem that we have with CPU idle is that CPU idle as such is invoked after RCUs have been put to idle. So once CPU idle invokes runtime PM, which has a bunch of traces, that again triggers RCU suspicious usage and idle CPU trace. So to avoid that, we have to use RCU non-idle. So genpd also has its own set of rules on what a genpd can contain. Non-IRQ safe devices, the genpds that we have today, can contain IRQ safe devices and non-IRQ safe devices. But when I say an IRQ safe device, it is a device that usually can power on, power off in an atomic context. CPU device is one such example. So normal genpds can have IRQ safe devices, but today we are introducing IRQ safe domain in the new genpd. Now the new IRQ safe domain also brings in a bunch of other restrictions that you can have only IRQ safe devices and IRQ safe subdomains. So the hierarchy coming down from a particular domain that is IRQ safe also have to be IRQ safe. So a domain that is IRQ safe that can be powered on, powered off in an atomic context will have devices that can be powered on, powered off in an atomic context, and other domains that can be powered on, powered off in an atomic context. So this is a new simple additional rule that we are adding to genpd. Well, this is work in progress. We've run into a lot of RCU stalls. I still have a bunch of them showing up once in a while. There is a discussion in the mailing list regarding runtime PM on where do you put runtime PM in the CPU hot plug path. So CPU hot plug path has been chopped up into a bunch of places. There is a generic code that is common across all architectures, and then there is architecture-specific CPU up and CPU down. So there's a discussion on where do we want to put this. Currently, it lies in the architecture-specific up and down. Runtime PM and genpd, they're not light frameworks, and to be called in from CPU idle raises a bunch of questions regarding performance. Do we even want to do this? What is the expense associated with running that? And RT kernel compatibility, I'll come to this later. So I've done a brief test on trying to figure out how much is calling CPU runtime from CPU idle path is going to add to the entire idle stack. And it seems like it's about 50 to 70 microseconds for the last CPU to power down the entire domain, or configure the domain to power off when the last CPU goes down, and about 70 to 90 microseconds for the first CPU when it comes up, goes and reconfigures the domain to remain active so that further WFIs don't actually power off the domain. So that's about 70 to 90 microseconds, and this still is pretty expensive in the CPU idle path, and that needs to be resolved, I guess, at some point. RT kernel has a limitation or a design choice wherein spin locks in RT kernel can sleep. So in general kernel, spin locks do not sleep. Spin locks spin and waiting for a resource, whereas in an RT kernel, spin locks are written as mutexes and therefore can sleep. So you got to use raw spin locks on an RT kernel. Now the question is, do we want to convert all the spin locks in genpd and runtime PM to raw spin locks, or how do we go about this problem? Now, while thinking about this, I also saw that there's a major constraint that we have with our solution. It's not a limitation, but it's a constraint that CPU devices, individual CPUs can only know the state, their runtime state better, accurately. I cannot know the state of another CPU. One CPU cannot know the state of another CPU. By the time you know the state of other CPU, the state of the CPU could have changed. So individual CPUs are the best places to determine what is an actual state. And for runtime PM, this has to be accurate. And so CPU devices can only tell runtime PM framework about their particular state, which means I'm going to access only my CPU device. So should I even need to lock? Runtime PM today runs with spin locks, and maybe we can even avoid that. But locks may not be avoidable completely, because at some point you're going to hit the domain and you're going to have to synchronize between multiple CPUs, at which point you would still need a lock. And maybe that can be converted into raw spin locks. I don't know. Any questions? Sure.
How this cooperate with the MCPM, or how this cooperate with the PSI? Because so far I still cannot get near what's the software layer for example, the genpd and the runtime.
So that's a good question. So the relationship with this to MCPM is that MCPM is much of a low level, wherein you don't even have MMUs and those things for the processor already set up. This is more at a higher level, wherein your CPU is still active, just going through, when you say active, it is still running, and it is going through CPU idle path, at which point it determines, hey, I'm the last core, what else can I turn off in the system? So it's looking for ways to reduce power at that point. And once it goes through and executes WFI, before it executes WFI is probably where it can call into MCPM. So it's a layer above MCPM. MCPM is very cache, very hardware specific, it's drilled down into the coherency level at all. So, and in some architectures where you don't have to deal with MCPM at all, because the firmware itself is able to do all that too. With relation to PSCI, I'm alluding to that later, maybe. Okay, I can explain that to you. So with PSCI, the firmware determines, there are two ways of PSCI. With PSCI 1.0, you could have the kernel determine what should be the state of the L2 cache, what should be the state of the coherency level. With PSCI 0.2 and platform coordinator, the firmware determines that. So with the firmware determination, you don't need many of these things. You could just call into the firmware, and the firmware will determine which is the last core, and then would determine can we power down the L2 or not. But with OS initiated, this is advantageous to do it through genpd. OS initiated is different from PSCI platform coordinated in a way that with OS initiated, you know exactly how much time you have to sleep. Because the timers and all known entities are all in Linux, you have a deterministic way of finding out when the next wake up is going to be for a particular CPU. With that, you can determine what will be the sleep time for all 4 CPUs in a cluster. That way, you can determine the state of L2 a little better than what your firmware is going to do. Your firmware is going to just go look at, hey, all 4 CPUs are down. All 4 CPUs have voted for L2 to be powered off. I'm just going to power off L2, which may not be beneficial in some cases where there might be an immediate wake up. So you've just lost a cache, a warm cache. So this will tie into PSCI is what we hope. The last man will be able to help determine what will be the state of L2, and that can be passed using a composite ID into PSCI.
So the question is, PSCI is only responsible for is only managed for the functionality. The untrust firmware. The untrust firmware only need to work for the functionality. For example, from the kernel, you send a request to firmware. Firmware will have to the response according to the request. In the kernel, just you mean they have the policy. You use the policy to select the correct idle state for the CPU or for the task. But the question is that before the CPU idle, the framework has to do that. So from my understanding, the genpd and the runtime PM is for the function layer. It's not for the policy layer, right?
It could be a policy too. So the CPU idle governor is a policy. CPU idle governor is a policy that determines what should be the state of the CPU. The genpd does the exact parallel for the cluster. And another domain could have another genpd that would do exact same level for the coherency level. So these are all policies that can be done in the user space, in the Linux kernel, as opposed to doing it in the firmware.
So that
So genpd framework also has this concept of governors. So before you actually change state, you can make domain-specific governors as well. So you could implement policy in the kernel, or if you have firmware that does all your policy, then your governor just doesn't have. You can just pass right off to whatever the firmware is, whether it's PSCI or something else. So the way the frameworks are structured, you can do it in the kernel if you want, or you can hand it off to firmware.
So I can understand later CPU idle. There have another governor means genpd.
That's correct. Yeah. Well, what would likely happen in this scenario is that CPU idle governors would basically be dumb. They wouldn't have to do much, and it's more the governor at the cluster level and the coherency domain level that actually becomes a little bit more tricky.
So if I understood this correctly, you said there's a hierarchy. So you'll have a genpd instance of some sort for the cluster, and then for the constituent elements in the cluster. And you said there's a policy element associated with each of these genpd instances.
It can be, yeah.
Okay, so to pull off something like CPU idle, where it sort of it does its timing heuristics and standard deviation to find out when to go into a deep idle state, you're going to have to decompose that policy into individual policy elements for the cluster and for the CPUs.
You have the ability to.
Okay.
You don't have to. So I mean, if you really want to go a long way, for example, you could do something like the CPU-specific governor could take a look at CPU local timers, for example, to see when the next CPU local timer is, decide how deep of a state it's going to be. If you want to go that fine, great, but you don't have to. I mean, I think for the first phase of this, we're probably envisioning more like the CPU level domains are probably just, they're not going to be very complicated. The policy will be more cluster level and coherency domain levels. But in theory, you could, at any level of genpd, you can have policy.
Okay. I suppose like ultimately this is going to be contrasted from a performance perspective against the status quo. So you will quite likely have to solve those problems in terms of how does it stack up against CPU idle for cluster idling. Okay, cool.
Sorry, one last one. The challenges that are coming with moving to genpd here, are they inherent to genpd and runtime PM, or is it the hierarchical nature? I guess I'm trying to mentally contrast this versus a theoretical rework of CPU idle to be hierarchical rather than flat view of the world.
The problems are exactly the same. The biggest problem is synchronizing between the last man down and the first man. So once you have a hierarchy in place, determining which CPU is going to be the last man and making sure that you have accurately done the reference counting and making sure you have a log in place to go and power off the domain. And in the meanwhile, another CPU comes up, cannot bypass this log and waits for this log. Once the log is released, goes and reconfigures the domain. So this concept is exactly the same for microarray.
Okay.
NPD already provides a way to do it, and we're trying to use that.
Okay, makes sense.
You're right, there's two choices. One would be to make CPU idle hierarchical, and it would end up looking exactly like runtime
Okay.
PM.
So we don't think any of this complexity is artificial, right? This is the real complexity that comes with dealing with the last man tracking and so forth.
Correct, yeah.
Thanks. Thanks.
Any other questions?
So one question was the additional latency that you mentioned. Can you sort of put that in perspective with latencies that you've seen? I mean, you know, how does that compare percentage-wise, or just in perspective to hardware latencies of CPUs for entry and exit of idle?
So on the same SoC that I recorded these numbers, average power down would be about 1.2 milliseconds. So you would do power down the CPU if you have time for at least 1.2 milliseconds. Your residency value for being in idle is 1.2 milliseconds. You would power down the CPU and bring it back up. To add to that is 50 milliseconds of just the runtime in addition. Yeah, so 50 milliseconds.
Wait a minute. So the residency. So your numbers were microseconds. The number that you mentioned, or the 1.2, is milliseconds. Okay.
You would need at least a millisecond before you can think about powering down. Otherwise, it's not efficient to power down the CPU.
Now, is that because it takes, I mean, on that platform, is that because it takes your entry and exit? If you go down and then immediately come back up, is that because that whole time is 1.2, or is that just because the energy break even of going down, being out, and then come back? So what's the actual latency of going in and coming out? Do you happen to know what those numbers are like?
Less than a millisecond, just close to a millisecond.
Okay.
The latency of powering down in the hardware, sorry, starting from CPU all the way to the hardware has about 5 microseconds for 1 way.
Okay.
5 microseconds.
Okay, so that helps kind of put those numbers into perspective. My other question was, so in the context, I'm been debating with some folks about the utility of having like CPU freak governors and how much policy we should have in SCED-tune and such, and there's been a lot of push towards eliminating all the knobs that are offered by CPU freaks. So I was interested to hear the direction that this might be going, where you could potentially go from having just the single CPU idle governor that we have today to governors at each individual level, which is going in the other direction and having potentially quite more complex policy. So I'm wondering, at LPC, did you guys get any pushback because of the complexity that might create?
There was pushback on complexity in general, but like I said, you don't have to have complexity at all these layers. It allows you to do it, but more than likely that's not what's going to happen. And I think everybody agrees that the ability for CPU idle to do this type of thing is lacking, which is why we have things like coupled idle states and a bunch of other interesting CPU idle governors and vendor trees. So I think there's the
Okay. So where are we today and what's the next step? So I'm just trying to give you a quick walkthrough of what we will be doing the next couple of months. So I think we have touched upon the first bullet here. It's regarding multiple states of genpd. Currently there is only on and off, and obviously when we talk about CPUs, they can have various states, retention states and different C states and so forth. So there's actually been RFC posted also on the list from Bay Libre guys. So that's probably something that we will look into on top of everything else that Lina's mentioned. And then we will also look into the ACPI 6 version and see how this maps, if our idea maps good to that. And our initial review from that is, yeah, could make sense. On the PSCI thing, I think we have discussed that, right? Do you want to add anything about that, Lina? Or? Yeah. Yeah, and so what's happened recently is that we have been working on genpd for quite a while, and we're keeping this CPU cluster management in mind. So and we have been discussing about the locking problem. So we're taking steps towards fixing that, and one part of that has already been merged and accepted. And the other thing is that the internal mechanism for how the generic power domain is dealing with intermediate states prevented us from having this CPU cluster management to deal with it. So we managed to get that out of the problem as well. And then the next bullet here is actually summarizing what we posted. I don't know, a month ago, 2 months ago, Lina posted this patch set that she has been describing here now. And we also have been thinking about the CPU PM notifiers and how to take the next step about improving those and possibly removing them. And perhaps we can use the runtime PM callbacks instead of these notifiers. And I don't know if you know about the details here, but currently there was an API for how to deal with C states and inside the generic power domain. And when certain devices certain drivers that deals with IO devices could notify or tell the CPU idle core about which C state to allow and not allow. And it wasn't scaling very well, and it's mostly from scaling point of view, it was a really bad API. But I guess Daniel Scanner, the maintainer of the CPU idle framework, didn't like it either because of performance problems with it. So we'll probably kill it, as there's no users of it right now. And we will have to think about something else and how to deal with this. Yeah. Okay. Yeah. So I think that's it. And maybe one more bullet I can add there is Lina's been talking about this latency or adding this latency when using runtime PM. And that's obviously also something that we will have to look into in real detail of how we can optimize the runtime PM execution paths, both in the runtime PM core but also in the generic power domain. So that's also something that we will have to look into, how to improve. Any further questions? Kevin, Lina, you want to add something?
Is it crazy bindings for this? You have DT bindings for this stuff?
The idea is that there shouldn't be any new DT bindings because there's already DT bindings for the CPU and for power domains. And so you just, in your CPU node, you just link to the, you do put a P handle to the power domain that you're in. And then, so the complexity will then be in the driver for that particular power domain has to know now about how to deal with CPUs. But there's, at this point, we went back and forth. The initial version of this, we actually had some bindings, but then in some more discussions on the list and with Lorenzo, we decided we probably don't need that.
This seems like a more logical place to encapsulate power data elements, right? In the sense that, so we have this problem with EAS where we want to express costing data in terms of the joule cost for running CPUs at different capacity states. And either you do that for each CPU, but if all CPUs are in a particular domain, then it makes more sense to attach the data to the domain they belong to. So it sounds like if we had grammar describing the domains, then that would be a better fit.
You could still do a binding, so when you do a binding for your power domain, so you have to write a driver for your cluster's power domain, you could have driver-specific properties to that binding that could declare properties that are unique to that power domain. So your new power domain binding would follow the existing binding, but you can expand it with optional properties. So it seems like that might be a good place for those
Right.
types of, that bit of data to fit well in the device tree. And in the right spot would be at the cluster level that you want that.
So that particular value is not needed for genpd. You are expected to be accessed from EAS or somewhere.
Yeah, so actually the whole topic about how do you express the costing data for the CPU side, which is what we're caring about right now, is an open topic. I mean, when we've spoken to people who are more conversant with DT than we are, in Lorenzo and the others, they've told us we've got our work cut out for us, right? Because it wasn't clear whether we can write on top of the OPP bindings to express, okay, frequency, but also, you know, what is the voltage association? Or someone mentioned that genpd might be a better fit, right? So just keen on understanding what exists today and seeing whether the path of least resistance for us to get the costing data into the main line would be something like this or not. I'm not sure really, but I like the fact that the hierarchy afforded by the genpd solution is a more natural fit for the power data. Right? So
It almost maps on the scheduler.
exactly.
Well, it should map exactly on the scheduler topology because it'll be, the scheduler topology will be driven out of the CPU node structure from the device tuner. So it'll be an exact, it should be an exact.
Cool, thanks.
Okay. Thank you. Okay.
On the fly? Does the genpd framework save more power than current framework?
Oh, does it save more power than the I don't know.
You don't know? Okay.
We'll say yes.
Yeah.
All we have is prototype on this right now.
Mm.
In theory, it gives you the opportunity to save much more power because in the way the CPU idle manages this right now is very inefficient.
Mm. Okay. So you don't have the power data.
We don't have any real data on actually using this right now, except for some experimental data from one SoC.
Okay. So what's the main benefit of this framework?
The main benefit is the ability to give you the flexibility to actually model the hierarchy of CPUs and clusters and even higher levels. There's no framework in the kernel to do that right now. Everybody's doing it in kind of ad hoc ways in their kernels now, but nothing upstream.
Okay. So that means if I try to save more power, using this framework, then I may need to develop some specific cluster driver.
Yeah, in the same way, of course, today you write a CPU idle driver that would handle your CPUs, and then you have to write some specific stuff that's specific to your SoC to handle the clusters and some key stuff. Rather than doing that in a custom CPU idle driver, that stuff would exist in a genpd driver that could actually be upstream and understood by others because of the hierarchical nature of it.
Okay, thank you.
But I mean, I think in the end, the performance would probably be the same, because what happens with these custom CPU idle drivers, they just get tuned and tuned and tuned until they work just how you want them. So you can't really, I don't know how you compare them directly.
I work for a smartphone, and the power saving is quite important. So maybe if there's some magic in this framework too.
Yeah, I don't know that there's any additional magic, but the benefit is that you'll be able to describe things in ways and also do it in drivers that we can actually upstream, whereas today we don't have any way to upstream these features because the CPU idle framework just doesn't handle it. And the CPU idle maintainers would just not take it. Who's probably here.
Can you change governors in runtime?
Pardon?
Can you change governors in runtime? Much like we do for CPU
I think we can in genpd, yeah. I don't remember. The governors are initialized once. But that wouldn't be too hard to fix, though, the way to take it. Yeah, that's a good point.
Why would you want to change the governor?
If you wanted to change policy or something, you would have different policy.
Performance versus power consumption.
I mean, it could be one governor with some knobs, or it could be governors that you can just plug and unplug.
Yeah.
Add that to the list. Any other questions?
We know that runtime PM have the callback function, right? We can set a register with this callback function. We also can set a register in the low level, the framework, for example, PM. We also can set a register in the MCPM callback function or in the PSI callback function for the SoC. So how we can distinguish the register setting? We need to use the runtime PM callback function, or should to use the low levels, the framework's callback function. It here.
So you would use the genpd callback functions to set the registers. So when the genpd callback function is called, you know it's the last CPU that's executing. So you have already determined whether you are the last CPU, and you now can go and configure the hardware to power off when that CPU goes down. So it's, in a way, it's similar to MCPM, but it is a little bit higher level.
But sometimes the scenario sometimes is complex. For example, when the CPU wants to power down, it will to set the register, right? And sometimes when the first man in the cluster want to wake up and to, for example, clear the register. So there have some risk condition between these. So this is my understanding why we need to use the MCPM or the PSI to do the to protect this condition. So there have another very special case is that the power down CPU is in the concurrency domain. That means you can use the spin lock, such like the mechanism. The wake up CPU it have not set the SMP bit. So that means that the CPU have not entered into the concurrency domain. So in this case, you cannot use the how do you say, the depend on the spin lock, this mechanism. So this is why MCPM use some of the state machine to protect this case. But you can see if you use the genpd, you can see all the CPUs always should to assumption is that the CPU should run into the cache concurrency domain. So that means you cannot to protect the race condition for the last man want to run into the, go to the power down states, and the first man want to enter the kernel, return back. So this is why I think that you register if you set in the genpd or the runtime PM, maybe you cannot protect for such kind scenario.
So in that case, it would probably just be a call to MCPM. This stuff would build on top of MCPM and those types of the SoCs that have that. So that last bit that has to happen there would have to be managed by MCPM, or the VLOC in MCPM handles this right. So it might be that this last genpd callback actually just triggers an MCPM call that actually would finalize it. But something like either we use MCPM or basically the similar locking mechanism in the genpd callback. But it has to do what MCPM does. That last man's name, first man.
So in that case, the genpd just use it as the governor or the policy, right? So all the